So today we will talk about differences, associations, and control variables. And most of the methods that we will discuss today, you all know. So you all know what correlations are, you all know what regression is and things like that. But we will talk about some things that many people sort of miss from that big picture. So you know what correlation is, but there are all kinds of little, contingencies or situations where just the simple correlation will not work. Or many of you have heard about, for example, control variables, but maybe not fully understand what they are and how they work. And so those are some of the things I want to cover today. And so some of the questions for today, the big questions will be, how do you know if X is associated, different from Y? Or does X affect Y? So those are relatively easy, but as I will show you, some of the basic methods that we all love and use and know may not be enough or may not be even suitable for analysis. But then it gets more complicated when you have, for example, some additional factors in the game. And so if you want to look at the effects of X on Y, but while controlling for like C, for example, control variable, or what if you have many predictors, or what if you have many outcomes, or what if you have many predictors and many outcomes. And so those things sometimes are, tricky. And so let's talk first about differences. So here are a couple of simple research questions. Like, for example, you want to know if the peer evaluations for men versus women are different, right? So you do some sort of, as part of your performance review for your employees, you do peer evaluations, and you want to know if there is a difference for gender. So maybe women perform better than men, or maybe women are more, I don't know, likable than men, or whatever the difference. Or, for example, if you are more kind of strategy person, the question can be, do profit margins differ by industry? So are they higher in IT versus manufacturing versus maybe law firms? So what methods would you use to test for these differences? Any suggestions? Anyone? Don't be shy. That's the simplest question and basically the basic, simple research design.
Quantitative methods, right?
Right. But what specific
are you talking about?
What specific method would
OLS regression?
Linear model.
Linear regression.
Yeah, so you're overthinking that. So we are talking about.
You're asking
to
do a survey or grab data from somewhere.
Right. So, but let's say you want to know if your men perform better than women, for example, right? And so you have 50 employees and 25 of them men, 25 of them women. And so you look at their annual peer evaluations, and you have 2 samples of 25, and you have each score for each, scores for each man and scores for each woman. And so you only want to know if men generally perform better than women. So what would you do? Like a very, very simple scenario.
The mean.
I was just going to say that, average.
Yeah, compare the means and the variances and the.
All right, so let's say, on average on a 5-point scale, men get a 4.1 and women get 4.2. Is it different or not? Is there a gender difference?
If it's
Are you trying to get a p-values or t-tests?
Yeah.
So somebody said statistical significance, but that's, it requires a method. At this time, I just calculated the average for each sample, and I have 2 numbers. So can you explain to me that significance thing that you just mentioned? What is that? How do you get it? Like, what method would you use to get that significance thing?
Talking about p-values, or you're talking about confidence intervals? Because you can kind of work with both.
So I've heard about p-values and confidence intervals, but I believe those are not methods. Those are some of the statistics.
You could run a t-test.
Yield.
T-test?
T-test. Somebody said t-test.
T-test.
Oh, that's interesting. Okay, so you can run a t-test, and the t-test will give you the p-value, and it will tell you if it's significant or not. Anything else?
Or one-way Anova.
You can do an Anova. That's very good. So let's talk about those things. So we will talk about t-test, d-score, Anova, and then multi-way frequency. So let me talk a little bit about them. So the simplest method would be the so-called d-score, or Cohen's d. So it's even simpler than the t-test. And so it allows you to compare 2 means. Like in our case, that would be the most suitable method. So it literally shows you have 2 samples, and you want to see if there is a difference between mean 1 and mean 2. And again, if you missed some of this stuff, so like, for example, here are 2 examples. So you have 2 samples, and as you can see in both samples.
If we're supposed to see something, we're not seeing it.
Yeah, we're not seeing anything. We haven't seen any slides yet. I was just wondering.
Sorry. Did I not show? Oh, okay. Here it is. Now you see them, right?
Yes, thank you.
Okay, sorry, yeah, I was giving you all these examples and I didn't realize I was not sharing my screen. So now you can see my slides. So you have two cases, case one and case two, two companies. And so let's say green are women, blue are men. And so in both cases, as you can see, the difference, the mean difference is precisely the same, but they have different distributions. So would you say that the green versus blue are different in case one versus case two, or similar or different in one, similar in the other one? So like in case one, is there a difference between green and blue?
Yes.
How
Depends
about
on sample
case
size.
two? Is there a difference between green and blue?
Yes.
Well, in terms of the mean difference, the difference is there. But when you look at the distribution, so clearly almost in case one, almost all green are to the left and almost all right are to the right. So if those are pure evaluations, if higher is better than lower, then in case one, you have virtually no overlap. So basically almost everybody who is in the blue sample is better than almost everybody who is in the green sample. But when you look at the second case, yes, there is a mean difference, but as you can see, almost all of them overlap. So there are almost as many sort of, green and almost as many blue that are basically overlapping. So the overlap is huge. And so if you ran that statistical significance thing that you mentioned, you probably will find no statistical difference in case two, but strong statistical significance in case one. And so for the D-score, it's a very simple, essentially, test. So it simply looks at the difference in means divided by pooled standard deviation. And here there's the formula for the pooled standard deviation, but usually it would be around the same. And so essentially it kind of accounts for those distributions. Because if you can imagine, in case two, let's say those distributions are even wider. If they were like, twice as wide as what you see, then the overlap would be almost 100%, even though there is a mean difference, but it wouldn't tell you much. So your distributions almost fully overlap. And in that case, probably the distribution will not be significant because, when you look at case two, there are many blue sample members, let's say, for example, men who are all the way to the left. And there are many green sample members who are all the way to the right. And yeah, on average, it seems like there is a difference, but it's probably not very significant because the two distributions overlap almost perfectly. And so there is this kind of rule of thumb for the D-score, which one is, like what's big, what's small, but this is not statistical significance per se, it's just simply, like, is it large or is it small? So essentially it tells you how the means, sort of relate to one another, accounting for the size of the standard deviation, for how wide those distributions are. So this is the most primitive method, but it's a very good one because it's simple, it's to the point. It's especially useful when you do, for example, meta-analysis. So the D-score is very useful for comparing differences. Likewise, if you wanted to look at, for example, political affiliations, differences among, I don't know, Democrats versus Republicans, or maybe religious affiliation, Christians versus, I don't know, Buddhists versus Muslims versus whatever the other religions are, or maybe different countries, Germans versus Americans. A very convenient, very simple, very straightforward method to compare those differences and get some sort of a sense of how significant they are. So very, very useful tool. But a more sophisticated method would be the so-called t-test. So it's very similar to D-scores, but the difference is that it gives you that p-value, it gives you that significance. And usually we say, if we have a chance of an error less than 5%, so if we can be 95% confident, we assume that there is a statistically significant difference. That cutoff, by the way, is very arbitrary. So why should it be 5% and not 4 or 6? But it's kind of accepted that if the p-value, the chance of an error is less than 5%, we kind of say we are comfortable and we can claim that the difference is true difference and not some sort of sampling problem. And so what's good about the t-test that it not only gives you the significance, but also there are all kinds of different sort of scenarios that you can use it for. So for example, you can test if there is a difference between your sample mean and some sort of an arbitrary value. Like for example, let's say you decide that 4 is your sort of cutoff. And so your sample score is 4.2, for example, on average. So is that a statistically significant difference from your, 0, so to speak, or from your any point on the scale or not? Or you can look at two samples, men versus women. And in this case, you can have independent samples. Let's say you have 30 men and 25 women, two completely different samples. Or you can look at one sample measured twice, like you have, let's say, for example, before and after difference. Maybe you looked at the peer evaluations before some training, and then there was some training, and then you look at it after, or maybe before COVID-19 and then after COVID-19. And so you have the same people and you have before and after. And so if you have the paired sample, it allows you to kind of more precisely estimate the difference. Plus, again, it can allow you to do so-called one-sided, two-sided analysis. So if you're not sure in which direction the difference should be, let's say men versus women, you have no prior hypothesis who's going to be better. So you do so-called two-sided test. But if you know that, for example, I don't know, COVID is going to make all kinds of things worse, and so you're looking, you know it's worse, you're just looking if it's much worse or not, then you can do so-called one-sided test, so if you know the directionality. So you have all those simple sort of contingencies, and the more you specify what you're doing, the more precisely you can estimate your sort of, you know, analysis, and the more, not only the more precisely you estimate the difference, but also your p-value becomes smaller. So kind of chances of an error decrease if you provide more specialization. And so here, yeah, go ahead, please.
Is it true that t-test is used more often in the research that we're reading? Why is that versus the D Cohen's test?
Well, so both of them use essentially the same logic and the same math. And since you asked, let me show you one thing here. I just opened the file. So I did a bunch of meta-analysis, and so here is my little Excel kind of cheat sheet. So if you can see it here, so all of these, or most of these methods, they essentially use the same math. So they essentially all look at mean and distribution. And so all of these formulas, when you look at them, they basically play with standard deviation and averages. And so we will talk about Anova, we'll talk about chi-square, we will talk about frequency analysis. So every time you talk about those kinds of differences, you almost always look at 2 points and then distribution of the sample. And so because they use more or less the same values and the same math, you can convert one into another, any one of them. So here, as you can see, I have sort of cheat sheets for R to D. So you can convert correlations to D scores. And so when you look at the formula, you can see the actual formula, but you know, it's essentially playing with those same things that we looked at. And so you account for the sample size, you account for the value, and one converts to another. Then D to R, chi-square to R, t-test to R, t-test to D, F for the Anova to R. So all of them are basically, can be converted one to another. If you want, I can send you this file so you have this sort of conversion table, but those are relatively simple formulas, and you know, right here, you just plug them in. And so let's say, for example, you're doing meta-analysis and you want to look at D scores, but one study gives you instead a correlation. So let's say you have a sample of 100 and the correlation is, let's say, 0.3. Boom, so that corresponds to the D score of 0.6. Or the other way around, you have a D score, but you want to get the correlation. So let's say you have 1,000, sample of 1,000, and your D score is 1.5. So that corresponds to correlation of 0.6. So no magic there. They kind of use similar logic each time comparing the same sort of distribution to slightly different formulas.
Voss, I would love for you to share that. I don't know about anybody else.
I'll send you the file. So that's
great.
Extremely useful, as I said, when you do the meta-analysis, because you want to put all your studies on the same matrix, so to speak, right? So you want to have all your values in one format. And usually we use correlations or D-scores for meta-analysis, but you can have all kinds of, whatever the study reports, so you can convert them all to the same statistics. And here you also have some additional corrections, like, for range restriction, or maybe sometimes they dichotomize, like high, low instead of 1, 2, 3, 4, 5. And so all of those can be easily corrected. The formulas sometimes get pretty long when you look at them, like here, but nothing super, like once you look at the formula, it all makes sense. So now, when it comes to t-test, so how do you know what's significant? I still remember the time when we were taught to use these kind of significance tables. So you take any statistics book, and at the end of the book, you will have this gigantic tables for different statistics sort of significance. And here is a snapshot of one of those tables specifically for the t-values. And so you choose the level at which you want to be looking at your significance. Like most of the time we look if it's two-tailed 0.05, and then you adjust for the degrees of freedom. So basically your sample size minus the number of parameters that you're estimating. So usually it's degrees of freedom, it would be sample size minus 1 if you're looking at, for example, relationship. And so as you probably know by heart now, that usually your difference, you know, for t-score, if it's 1.95 and higher, it's statistically significant. So it corresponds to, you know, like if your t-score is 1.96, then it corresponds to the p-value of 0.05. So it's significant. So nothing difficult. Any textbook has these tables, and they have them for F statistics, for chi-square statistics, for T and Z scores. And usually it's like 3-4 pages, depending on how long it goes. And then after like some sample size, they kind of stop changing. So they become almost the same. So once you hit about 100, it doesn't really change. So you don't really need to go beyond that. But you can also use Excel for that. Like, for example, I'm not sure if you ever played with Excel, but Excel allows you to use all those, you know, if you go into statistical significance, you have like, for example, T inverse. So this will give you the p-value for yours. So for example, if you have the probability you want to get 0.05 and you have degrees of freedom 100, so it gives you the t-score for this situation. Or you can go the other way around. So if it's not inverse, if it's a regular t-value, so I think it would be like this. And in this case, it makes no sense, but yeah, so I need to go, sorry. I need to do the other way around. So if you want to see if your t-value is statistical significant, so you do t distribution to two-sided. And so you do x, let's say, for example, in your case, t would be 2.0. And degrees of freedom, let's say you have a sample of 200 or 100. So in this case, your p-value is 0.04. And so that gives you, sorry if it was too small. And so that's your p-value. So if you want to change it, so let's say, for example, your t-score is 1.5, but your sample size is 10. So for that one, it's not significant, right? So you get the p-value of, you know, but if it's, let's say, if it's, for example, 2.2 with a sample of 10, so almost significant, right? And then if your sample size increases to, let's say, 50, it will probably become significant, yeah. So it's less than 0.5. So you don't even need to use the tables anymore, like the one I have here. You just go to Excel and you either get the t distribution. So if you use the t statistics, you plug in the t-value and sample size, and it gives you the probability, so the p-value, or the other way around, to get the p-value and it calculates your statistics, you know, t-score. So, and there are also countless online calculators for t-test. Again, if you go to, for example, any, you know, website, so you just say t-test online calculator. And so there will be literally hundreds of them. I'll just open the first one that comes here. And so in this case, you can plug in the values. Let's say you have 2 samples of, let's say, 50 samples. And so you just plug in some numbers, some random numbers here. And so you have another sample here, for example. So you have a bunch of other values. And then you just click enter, and it should give you the number. So calculate, so it's 2 group, calculate now, and it gives you all of this. So it gives you mean for each group, but then in the end, where is my t-value? So the t is 0.021, so it's not significant. So as you can see here, it's not. So it crosses the 0 boundary, and so it's just not a good one. So your p-value is almost 1, so, and you want it to be 0.05 or smaller. So that's for quick calculations, and then you will find always calculators that, you know, you just plug in the values. So you plug in, do we have t-test calculator? So this one also wants the samples, but some of them allow you to just plug in mean 1, mean 2, standard deviation 1, standard deviation 2, and then it just gives you a quick calculation. You don't even need, like, for example, this one, yeah. So you just plug, like, let's say, for example, first mean gives you 4.1 and standard deviation of, let's say, 0.5, and you have 50 men. And the second sample is 4.0 and standard deviation is 1.0, and you have 15 men. So do you think it's going to be significant difference or not? Well, let's check. So in here you get, where's the value? So you have standard deviation of variance. Where's the p-value here? Trying to see where they put it. Yeah, so t-statistics is 1.05, so it's not significant. So the p-value is less, more than, yeah, so 0.29, right? So, but if I increase this difference, let's say, for example, to 4.5, and I make this sample bigger, let's say, for example, 45, I bet it will be significant. And sure enough, as you can see, the p-value is less than 2. So you got your, you know. So very simple, available all the time. So if you want to do a quick test sometime, you have all that available online. Make sense? Now, when we get to Anova, anyone knows how Anova is different from t-test? Oh, and I see we have comments here. Sorry, I was not paying attention. So anyone knows how Anova is different from the t-test? Anyone wants to get the gold star? Come on, don't be shy. Give me one idea.
Isn't it where you choose whether it's a one tail or a two tail and how you're comparing the two means?
No, the biggest difference is that
I think-
yes, go ahead, Mark.
I think t-tests are limited to 2 groups, right?
Yeah.
And Anova, you can go more than 2.
Yeah, unlimited. So the biggest difference is that Anova is for 3 or more. It can do 2 as well, but it can go as many as you want. And a t-test only does 2. So it's either 2 samples or sample versus some value. But there are also a couple of things in Anova that that allow you to do things that t-test does not allow you to do. So one, Anova allows you not only to test multiple samples at the same time, but it also tells you if at least one pair of samples is different, and then allows you to determine which ones are different, which ones are not. But the best part of Anova is so-called, it allows you to calculate the variance between groups versus variance within groups. And I'll explain that in a second. It's a very, very powerful sort of technique and statistics. I used it myself in a couple of studies, and very useful here. So the sort of within versus between variance is, basically how far away are the group means versus how spread the variance is within the group. And so nothing super difficult here, but I'll show you an example like this. So for example, when you look at this second case, is there more variance within groups or between groups?
Between.
Right, so almost all variance is between groups, right? So that the groups almost don't overlap at all. Whereas in case 1, as you can see, there is a lot of variance within groups and a lot of variance between groups. So groups overlap a lot, and so you don't have that clean separation into groups. And that can come in very handy when you get to some interesting questions. Like, let me give you a couple of examples here. So I'll give you a real study that I published not long ago. Well, it's been a few years, but then I also followed up with a Harvard Business Review study. So, and for that study, the question was, is country a good container for culture? So I started that paper with almost 1 page of quotes, how either titles of the papers or how in the discussion in the papers, people talk about sort of cultures like German culture or American culture. So they would say, like, for example, we compare certain behaviors or preferences in 2 cultures. And then you read about the sample and they say, well, we compare Germans to Americans, for example, or I don't know, Australians to, I don't know, Brazilians. And so the question was, does it make sense to talk about German culture versus American culture? So we know that we can test the difference between 2 cultures, but what if you have, let's say, for example, 40 countries? And so we wanted to see if sort of the country is a good kind of proxy or container for culture. Do cultures as cultural values kind of cluster within countries or not? And so this is where we looked at something like this. So essentially, if we want to talk about cultures as countries and countries as cultures, then we need a picture like what I have here. So we need to see that, for example, let's say if we define culture as individualism, collectivism, then, Americans need to be all individualists, and then Germans maybe will be all in the middle, and maybe then China will be all collectivist. In that case, yes, it makes sense to talk about countries as cultures, because in this case, there is a clear separation in culture by country. But is it really the case? And so what we did was, we looked at basically distribution of values within countries versus between countries. And so some people sort of recognize that, no, not all Americans are different from, for example, Germans. There may be regions within the United States. Like there is a big difference between like the United States, for example, Hawaii versus New York, the United States, or maybe New York versus Texas. But again, or maybe same thing for Canada, like, Francophone versus Anglophone Canada. It's not allophone, anglophone. Or maybe sometimes, like German or French or Italian section of Switzerland. But the problem here is that you cannot really use geography or slice geography too much, because, you can look at one skyscraper in Manhattan and you will probably see very different values, like in the CEO suite versus, salary workers versus the guys in the mailroom. So they may have very different sets of values and cultures and work practices and, work style and, values in life and all kinds of things. And so what we did was we looked at cultural values, individualism, power distance, all those things that we discussed, but we wanted to see if those values cluster better within countries or, for example, within gender groups, men versus women, or within age cohorts, young versus old versus medium age, or generations like baby boomers versus generation X, Y, Zoomers, whatever you get, or occupations or socioeconomic status. And we even looked at, for example, country characteristics. So maybe it's not nationality, maybe it's like rich countries versus poor countries, or maybe it's, corrupt countries versus countries without corruption, or things like that. And so these are some of the results. So when you look at those between variants, here you have the between group variance. And so when you look at culture, so what you will see is that within you have most of the variance, and between not really that much. So like, for example, when you look at power distance, so only 21% of the variance is within countries. So the picture basically looked like this. So the area, in fact, not even like this, it's even more overlapping. So 80 to 85% to 90% of all variance is kind of shared. So it falls in these overlapping categories. And so it tells me that country is not a very good container for culture because almost all variance is within countries and not between. But then when you look at, for example, occupation, it's a little bit better. It's not, occupation will not explain everything, but it gives you, like for example, for power distance, it gives you 50% of within and 50% between. So we looked at 7 different occupations there. We had like scientists, we had managers, we had salary employers, we had entrepreneurs. I don't remember all 7 categories, but those were much more meaningful containers for cultural values than country. Likewise, when you look, for example, at the employment status, apparently people who are employed versus people who are unemployed, it tells you a lot about power distance, for example. Not so much about individualism for some reason though. And so the conclusion was that no, country is not a very good sort of container for culture. It makes more sense not to talk about cultures of Germany or the United States or Canada, but more about cultures of professions or cultures of rich versus poor, or countries of those born in the 60s versus 2000s, or those living in the free versus suppressed countries, or corrupt versus transparent, and so on and so on. And so this is something that you wouldn't be able to do with a t-test or d-score, so it gives you this wonderful additional layer of interesting statistics. If that makes sense. Any comments or questions about that? All right, now let's get into something. Yeah, someone wanted to say something?
Sorry, I did. On your last slide, of course, you just unshared it.
Oh, yes. I'll go back. Yeah, this one?
One back.
One back, yeah.
Thank you. I just was curious as to decade study conducted, the last one. Is that your own study?
Oh, that was, since it was a meta-analysis, so we looked at the year when the study was published. And so we wanted to see, we thought maybe, maybe like 50 years ago, maybe there was a lot of, like country maybe was a good container for culture. But maybe now the world is becoming more globalized and it's less relevant. And so we had 4 decades. I believe we had the 60s, 70s, 80s, and 90s at that time. So it was published a few years ago. We could have had 2010s, but I think it was stopping in the 2000s. Okay. And so essentially what we found that, yes, so it's still a lot variation within decades than between decades. And so no, that was not a very good container either. So we thought maybe, as I said, like maybe 40 years ago, people traveled less and maybe sort of, that year meant a lot, but no. It seems like, the employment status and occupation are most meaningful. So if you want to talk about, cultures of professions or employed versus unemployed, but even here, like if you look at some of the dimensions, even here, it's not really that useful. And by the way, there have been a bunch of other studies. There have been also many studies that did the same type of analysis and they showed the same thing. So it really makes no sense to talk about, for example, culture of the United States versus Canada. So it really makes no sense, like it's not a meaningful container.
Okay, thanks for explaining that. So cool.
All right, so let's talk a little bit more interesting cases here. So differences and correlations are easy, and associations, but what if you have your data that are not normally distributed? So let's say you want to look at the associations or some other, like does X affect Y? But what if you have not normally distributed data that are, like your age or weight or income, but you have like rank data? Let's say you, for example, have university rankings or company rankings. Or what if you have some sort of like ratio data or percentages? So those are not, they do not conform to your assumptions of correlations, t-tests that, as you remember, assume that your data are normally distributed, continuous, your errors are random. So it's a very, specific type of data that they're designed to work with. So the question then becomes, can you use what kind of methods you can use to assess either associations or differences when you have these kinds of data abnormalities? And so then you have a very, different set of analyses that you can use here. And so I'll give you a couple of examples here and then we'll talk about them. So for example, you want to look at the association, and let's say you want to look at the relationship between the GPA and on-the-job effort. So do people who had higher GPA in school, do they work harder at work? Or does your firm size predict firm marginal profit or profit margins? So do bigger firms have higher profit margins? And so obviously for this one, you would be using correlations, but there are also some special cases where the regular correlation may not work. And so we'll discuss those things. So one for correlations. I mean, obviously all of you know what correlation is. And when we say correlation, we usually mean Pearson's product moment correlation, right? And so it's a wonderful, great method. But the problem with it, what many people do not realize is that it has a bunch of assumptions. So it assumes that you have paired variables. So you have two lines, of data or two columns of data. And so you have observations in every row. Second, it assumes that your variables are continuous. Then it assumes that your data are normally distributed, and then you don't have outliers. And it assumes that you have linear relationship and you have so-called homoscedasticity. Anyone knows what homoscedasticity is? I'll give you a gold star if you tell me what that is.
Isn't that when like the graph like expands like really high, like the further you go up it? So you have a lot of variance between everything the further along you move the x-axis?
Not really. So it shows that
I give it a shot.
Variances.
Somebody said variance. What was that?
The variance is normally distributed across both variables.
Not normally, but equally.
Right, and the error?
It's similarly.
So it would be something
Similarly.
like this.
Sorry.
So this is the case for heteroscedasticity.
That's what I was trying to say. I didn't say it very well. That's what I was trying to say.
Let's say you're looking at GPA versus performance. And in this case, at the low level of GPA and performance, the variance is very small. But when you get into high GPA, your performance becomes, the variance becomes very high. And so again, normal correlation assumes that this line is kind of uniform across the entire range. So your variance is kind of more straight and equal along the entire range. But again, it's not always the case. And when that's not the case, you have two alternative methods to assess relationships. One, you can use Spearman's R or Spearman's correlation, and then you can also use Kendall's tau. And so they use slightly different math. And to be honest, the correlations will not be that different. If you use a SPSS, R, Stata, all of them allow you to calculate Pearson's correlation, but Spearman and Kendall tau and Spearman rho, I guess is marked. And you will see that they're very similar, but still there will be significant differences. And so if you have those non-parametric data, you will not be allowed to use Pearson's R. And in that case, you have to use one of these two other methods. And so usually Kendall's tau is sort of preferred because it handles better smaller sample sizes. It deals well with outliers. It doesn't have to have the same number of observations in each column. So it gives you all kinds of different things, but it usually yields you somewhat smaller numbers. And you have to take that into account when you do the interpretation. So, but these two,
Boss,
yes.
Boss, you're not sharing your screen again.
Oh, sorry, again, my mistake, yeah. So there was
You have
really
good slides, we'd like to see.
So there was nothing, here to show. All I'm saying is that there are three different indices to assess a relationship. And so if you have nice, normally distributed data you use just regular correlation. But if the data are not meeting all these assumptions, then you have to use one of these two other methods. And so Spearman's row would be usually preferred. But if you have a small n, or if you have outliers, or if you have other abnormalities, then you have to use Kendall's tau. So like, for example, let's say you want to look at the correlation between gender and performance. And you have two columns, and one is gender, male, female. And let's say you code them as 1 and 2. Let's say men are 1 and women are 2. And then you have performance. Technically, you can plug that into the into your correlation table, and it will give you some sort of a result. But it would be not an accurate estimate because of those abnormalities with the data that Pearson's R assumed that you have. And so in that case, you would need to use this alternative method, right? So nothing super difficult, but remember that there are different methods. And when the time comes, all you need to do is just go to, for example, let's say you're using Stata and you don't remember how to do it. So all you do is you just type Spearman's R and then Spearman's R Stata command, for example, and it will give you the command. And so it will be, instead of just the regular Corel, it will give you, does it give you the command here somewhere? The language, I'm trying to find, seems like SPSS, no, Stata. So I'm trying to see what the command is. Honestly, I don't remember this one by heart. It just literally calls Spearman. And we can even do a quick sort of analysis here. So for example, you want to see what the correlation is. Let's say, for example, you have gender and then you have performance, right? And so, for example, you have 1 for men and you have whatever number of men. You have 2 for women. You have, so many women. It doesn't really matter how many you have here. And then you have some sort of performance numbers. So I'll just copy some random numbers. And so I'll just do this a bunch of times. And then maybe I'll do something like this. And then 1, 2, 3. And so we can very quickly check if there is any difference in this case. So for example, this is my correlation. So I will go to Stata. Where's my Stata? Right here. And I'll just clear whatever I was doing here. I will type my values. And I have performance and male, female. And so let's say I don't really know how it works. And so I go with the regular correlation. So first I will take a look at the data just simply to see what I have here. So I have gender, I have performance, I have mean, everything looks fine. But now I want to run the correlation. And so I run regular correlation between gender and performance. The correlation is negative. So we had 1 for men, 2 for women. So it seems like men, what is it? Negative correlation. It means that women perform lower than men, whatever that measure is, right? But so we got some correlation. But then let's see if Spearman will give us the same index. So we'll look again at gender versus performance. In this case, it's actually the opposite. So it gives us a positive correlation. So go figure. So not only it is stronger, but it's also positive. So, and the probability, let's see if the probability is significant in both cases. Power core, in the first case, it gives us the significance, performance and gender, and you have your significance. So it's not significant. So when you look at the regular correlation, it's not significant. It's more than 0.05. But then we'll look at the Spearman's row, and as you can see, it's significant. The only thing I don't understand why the sign is reversed. So I wonder if it's really different index, or it just simply looks at the ranks differently. And I think it probably assumes that it's the lower the number, the higher the rank. So it probably assumes that it's 1 is better than, number 1 is better than number 2. And so I think that's why it reversed the index. But as you can see, in this case, it is statistically significant because it recognizes these non-parametric, deviation from the assumptions in the data. And so if you use the proper index, you will catch that relationship better, and you will have a lower chance of the type 2 error. So.
Said to use Kendall's for a low n. But what?
Yes, and so yeah, Kendall's tau gives you an even better estimate when you have a small n, like if you have like less than 10 cases, or if you have serious outliers, or many values, many cases are with the same value. I'm not sure why it matters, but apparently sometimes it can mess up your results, and so those will give you. And so the number itself will be lower, but the significance is calculated slightly different. So you just look at the p-value in that case. So you just kind of you should keep that in mind. So, all right. Now, what if, and that's another common situation, what if one of both of your variables are nominal categories? Like, for example, you want to look at the relationship between party affiliation and, let's say, I don't know, performance, or I don't know, absenteeism. So are Republicans more diligent than Democrats? Are they more likely to miss days at work? So what would you do in this case? How would you look at those associations?
You would dummy value them?
That's an option. So you can do a dummy value. And so you would do, like, for example, 1 is Republican, 2 is Democrat. And then in that case, you don't use their Pearson's correlation, you use Spearman or Kendall-Tao. That's one option. That's very good. And so in that case, you can just look at the correlation index. What if you have Republicans, Democrats, and independents? What do you do in this case?
0, 1, 2.
Use a chi-square.
Chi-square or Anova. Anova allows you to compare multiple samples, right? So you would have 1, 2, 3. So you basically, and Anova allows you to work either with a continuous variable or with a categorical variable. So you just have, Democrat. I don't even think you need to convert it to numbers. So with Anova, you just literally use string variables: Democrat, Democrat, Republican, Republican, Democrat, Independent, and it will give you by category the differences. So that's another option. So Anova would be probably the easiest way to do it. How about if one of both variables represent a frequency or percentages or ratios in that matter? What do you do in that case?
Frequency or ratios.
Can you ask that question a different way? I don't understand what you're asking.
So your variables are not continuous, but are percentages or ratios. So like, it would be, it's a different type of variable. And again, it's not suitable for regular correlation because they would not be normally distributed, or, they're just a different type of variable. So what you do in this case, one, obviously, again, we talked about how Spearman's row and Kendall's tau can do ordinal, interval, or ratio data. But if you have more than 3 categories, Anova will not do. So what you can do is you can do so-called multi-wave frequency analysis. And if you got your Tabachnik and Fidel textbook, it actually has a whole section on multi-wave frequency analysis. So it's a different method. It's probably not likely that you will need to do that. But again, these are different types of data. And so your regular correlation just will not do in this case. All right, now let's get into something more interesting. So what if you have a more complicated picture? So what if you have more than 2 variables? So sort of you want to look at the relationship between 2, but you want to control for some other factors. Like, for example, you want to see if the college GPA affects or predicts on-the-job effort, but you want to control for age, education level, and compensation level. So you recognize that maybe it's not all about college GPA. You want to control for those other factors. Or if you want to predict, for example, if the firm size, age, and capitalization of the company and industry predict profit margins. So again, let's say you want to look at the size, firm size, but you want to control some of your firms are old, some are young. Some have a lot of capitalization, others have little. Some have a big market share and some have a small market share. So how do you analyze the effect of size when your sample has all those other differences and you want to kind of control for them? Anyone knows how to do that? And I'll give you an example in a minute that will sort of explain that well.
You just use multiple regression?
You use multiple regression, exactly. And so I remember when I took my first statistics class, I was trying to remember sort of, or understand what that means when the professor says control for. Like I could not understand, like, how do you, like, I don't see the window for the control. But the point there is that when you add all of the variables to the model, so each of those effects that you see, it's always controlling for all of the other variables in the model. So it doesn't really care which one you're most interested in. So all of them give you so-called partial correlations. So if you have like 5 predictors, then each of those regression indices is, you know, the effect of this corresponding predictor controlling for the other 4 predictors. And so I'll give you a couple of examples just so you know what that is. So very interesting stuff. So for example, I was reviewing a real paper about 3 days ago, and I recommended a rejection. So they sent it to me because the paper dealt with culture. And so the paper was about the effects of culture on entrepreneurship, essentially, or entrepreneurial behavior. So they wanted to predict or wanted to claim that individualism values or individualist values predict the number of startups in the country. And so they had a multi-country sample, and they basically looked at a bunch of countries and looked at how the country individualism level correlates with the number of startups per 1,000 people. So, and I think the theory was that individualist values are more, you know, people with individualist values are more prone to engage in sort of capitalist behaviors. So they're more likely to start businesses. And so that's why we see, for example, a capitalist country and a very individualist country like the United States has more startups than, for example, collectivist cultures like, I don't know, maybe Ukraine, for example. And so they had 2 variables, essentially. It was a little bit more complicated, but basically 2 variables. So they had individualism, collectivism, and they looked for each country at the number of startups per 100 people. So how would you test this hypothesis?
Back to Anova again?
Well, one thing you can do is, you said Anova, that would be suitable, but the simplest way would be literally just take a correlation between the 2, right? So just look at the correlation between culture or individualism, collectivism on a 100-point scale and the number of startups per 100 people. Or if you want to be more sophisticated, you can use a regression analysis with 1 predictor, right? So, and I didn't like that. I said it's not a very good method. So we could look at the correlation, but I didn't like it. And so what I'm going to do here is, let me go to my file here. So let me open the file and I will do it with you and we'll see if we can sort of together crack this.
So they didn't control for anything? Is that what you're saying? They didn't have any?
Yes, that's precisely what I'm saying. So they have a bunch of variables here, as you can see, individualism, and then entrepreneurial behavior, startups, and stuff like that. And so let's do a correlation.
We don't see that.
I don't know. I don't think we're looking at what you are looking at.
Oh, sorry, let me do again.
You're looking at Stata.
Yeah, Stata, that's exactly what I wanted to do, yeah. So I opened the file here. So in the file we have, let's do the summary.
Oh, yeah, there it is. Yeah, in the top
So
right
we
corner.
have, well, so we want to have 2 variables. So we want to look at the number of startups and we want to look at individualism. And so you have 45 countries, you have 45 observations for each of those. You have the averages, standard deviations and stuff like that. And so essentially what they did, they looked at correlations, right? And so they looked at correlations between the number of startups and the individualism, collectivism. And voila.
In 45 countries? Is 45 the number of countries?
45 countries, yes. And so they found a positive correlation of 0.35, right? Approximately. And so they looked even at significance. So I'll do the significance here. And so we will do the same thing for number of startups predicted by individualism, and I'll do significant. So looking at the results here, you have the significance p-value. So is there a positive correlation or significant correlation or not?
Yes.
So it looks like, yeah, voila. So we predicted startups by individualism. So we can say that individualist cultures predict startups. And I said, no, it's BS. It's not good. Why is it not good? Why would you not be happy as a reviewer?
It's so simplistic. I mean, it's ridiculous to look at the, I mean, you have to control for some things.
Exactly.
Right?
What would you control for?
Think about, well, I would think about things like tax levels, you know, incentives to, you know, what's the likelihood of your company being taken out from under you by the state?
Very good. Yeah. Well, one thing that comes to my mind immediately
is taxes.
Was that taxes?
And taxes.
Yeah, but one thing that comes to my mind immediately, I mean, I'm a culture guy, and I know that individualism and collectivism correlate nearly perfectly with economy, with GDP, and so GDP per capita. And so I immediately suspect, well, maybe it's not about culture, maybe it's about economic development of the nation. And so let's do a regression here. So first we will predict so we will predict number of startups based on individualism. So we do a regression. And here is your regression. So you've seen, I'm not sure you probably used R, but I guess it's the same thing. So I can say that I predict or explain 10% of variance, right? So my R squared is, 12% of variance, everything looks perfect. And if you do a regression like they did, your p-value is 0.01 or 0.02. It looks like I predicted the entrepreneurial behavior based on culture. But I'm smart, I know that it's not the full picture. So I would say, well, why don't you control for economy? And so let's try to do that. So we will do the same thing, but we add one more variable, which is GDP, right? And so we will control for GDP per capita. Boom, the whole picture changes. All of a sudden your culture is not significant, and turns out that everything is explained by GDP per capita. So it's all about economy. But then, so like, for example, Susan said, well, maybe it's not economy. Susan, what else did you say we want to control for?
Oh, the taxes.
Level of taxes, what else?
Level of taxes. The
Could be education.
Yeah, so I plugged in a few.
Infrastructure. I mean, that's maybe GDP too. Infrastructure. Can you get your goods? Can you know,
exactly
the roads to transport them?
So I quickly, literally created a sample size. So I took about 45 countries. I got the number of startups, individualism, collectivism, but I also added level of education as measured by percentage of GDP that goes to education. I looked at the corruption index, and I looked at ease of doing business as a proxy. I used the number of days you need to spend to create a business. And so when you add all of those, this is what I get. So all of a sudden, individualism, collectivism is not significant, even close. Like it's not even, even not on the radar. GDP turns out not significant either. So education kind of gets there, but it seems like it's more about corruption and more importantly, ease of doing business. If I can open a business in 2 days, then yeah, I'll open a business. And if I need, like in Ukraine, it's like half a year to open a business. If it takes half a year, I mean, obviously nobody is going to be spending time on that. And so as you can see, the coefficient is negative here, meaning that the more days it takes to open a business, the fewer people will take, will try to start a business. And so once you add all of those, you can now compare them more or less directly, and you see a very different picture. So it turns out culture doesn't matter, and even the economy doesn't matter that I thought would be, an explanation. And even education that I thought would matter if you kind of add it without the other controls, it comes out significant. But it seems like it's more about corruption and it's more about ease of doing business. So those things really matter. And so that's where the whole story is. And so I said, no, I will reject the paper because even though you found a correlation and it's statistically significant, unless you control for those other factors, it just makes no sense. And so once you look at this here, you see that all of these variables together explain like 70% of variance. I mean, there is still something going on. There are some other factors that I did not account for, but it's a big, big difference. And this picture is much, much better explained by doing it like that.
Regulation would be.
Sorry, go ahead.
I was just saying regulation. A lot of companies moving out of California right now because high taxes and just lots of laws and rules. It's not only hard to open a business, but it's hard to. There's just a lot of bureaucracy.
Exactly. And yeah, I should have probably added more on tax level by country. It becomes a little bit more complicated. I guess you need to look at the effective tax rate because there are so many different ones. But yes, you can extend that model even further. But yeah, the point was that just because somebody found a correlation between two variables and it's statistically significant, it's not always the full story or not always the story. So once you control for those other factors, it becomes a much more different picture, right? So, so this is what I did here, and we did it. Yeah. So could there be a better explanation? So we looked at all these other factors, and so we found that it's a little bit more complicated. Now, sometimes, and this one is for some reason it almost never makes into the textbooks, but sometimes you want to look at the sort of relationship between a group of variables and a group of variables. And so technically, you can create like an index, composite index, formative index. Like for example, let's say you want to see if there is a correlation between sort of doing the right thing and showing good performance. Like for example, you believe that people who had high GPA in school, who have high IQ, who have a lot of work experience, those people are going to show better performance as measured by peer evaluations. They work longer hours, they churn out more units of product per hour, for example, productivity. And so you can look at each of these one by one, but you really want to have, like, for example, like your workers with a great resume, so to speak. So those who have high GPA, high IQ, high everything, and then do they show good performance? And again, you don't want to use one indicator of performance. You want to look at all of them at the same time. Or again, if you do more strategy work, so for example, you want to see if companies with certain characteristics show better performance. And so for the certain characteristics, you look at size, age, market share, and maybe if they are in high-tech industry. And then for the performance, you want to look at, for example, profit margins, employee satisfaction, and retention, employee retention. And so again, if you wanted to use correlation, you can look at each of these one by one, but you have so many different combinations and it's not really an kind of elegant method. If you wanted to look at the regression as we showed here, again, it becomes a little bit more complicated because you can only have one outcome in regression, one variable. And here you want to look at like 4 different measures of success. So what would you do in this case? How would you do it?
Structural equation modeling.
Yeah, but what would it look like if you do structural equation? I think you can do structural equation, but it will look something like, you know, let me see, let me just get it. So for the structural equation, you will have something like this, I assume, right? You kind of have 1, 2, 3 predictors. You have 1, 2, 3 outcomes. But how would you, let me do it. How would you connect them in structural equation? So like, would it be everything relates to everything, or how would you do it?
Like factor analysis?
Well, one way you can do it, you can sort of have it like this, right? And I think that would work. But again, it sort of becomes a little bit complicated and you're looking really only at this specific relationship that interests you, right? But one in the middle. But here it's sort of, I don't know, it's not the most elegant, not the most parsimonious ways to measure it, so to speak. So is there any better way to do it, anyone, than this? There is this very nice and neat method called canonical correlation. And you really almost never see it, but I personally find it very, very powerful and very suitable for many analyses. And so for canonical correlation, it literally allows you to look at correlation between many predictors and many outcomes at the same time. So it allows you to not only plug in a bunch of predictors and a bunch of outcomes, but it does recognize that these are all, for example, measures of how good the person is, so to speak, and these are all measures of how well the person performs. Or these all are characteristics of the company, and these all are measures of company performance. And so it allows you to skip this step that I showed you here. So it allows you to skip the step of either creating this complicated model like this, or allows you to skip the step of creating the composite measures where you sort of have some sort of like a formative index for the whole, performance indicator. And so it literally just gives you the coefficient, for the overall relationship between those 2 blocks, but it also gives you then data on each of those characteristics. So it will tell you, like, for example, maybe the firm size matters, but firm age does not matter as much. And so it predicts, your predictive power, and it gives you a much neater, nice, set of results, right?
And that, will that give you, so in one fell swoop, that'll give you the correlate, you don't have to have anything before that. And you can just have a theory supported obviously by the theories, but you don't have to do any other analysis or checking of this, because a lot of the stuff we have to do all sorts of other processes beforehand to make sure that.
Well, you still check your data for quality and everything, but it doesn't require that you create like a composite measure and then run all those factor analyses or principal component analysis. It's especially useful when you have sort of predictors or outcomes that do not necessarily belong together easily. Like, it can be, for example, number of days the person was absent from work as a performance measure, maybe number of units sold, maybe it would be, I don't know, satisfaction. Like, you can't really put them in one block because, it's not like it's the same questions about the same construct. So those are not very easy to sort of to consolidate because each of them is measured on a different scale. Like, you cannot take an average across satisfaction, performance, peer evaluations, sales. Like, those are very different variables and you cannot just simply add them. It becomes a little bit more complicated. But canonical correlation doesn't care. So you can have all those characteristics together and it just looks at them sort of, it recognizes that they belong to the same block, but they're different measures. So that makes sense. So I don't really see much use of canonical correlation, and that's almost unfortunate because in most of the cases, you don't really work with one variable at a time. You have, well, if you have an index, maybe that's fine, but in many cases you have those kind of blocks. Anyway, so when we get to the more specific examples, So for each of these methods, you have a chapter in your Tabachnik and Fidel. And then I also gave you a couple of articles here. So I'm not sure if you had a chance to look at, let me see if I can show you. So I updated the syllabus a little bit. And so what I did in the syllabus, let me go here. So for each of the lectures, I added a little bit more readings than you had in the beginning, but also to save you time, I added the actual papers in the folder. And you have the link for the whole thing in the email that I sent you, and I believe at the beginning of the syllabus here. But you also have the link directly to each paper right here in the syllabus. So you don't even need to go anywhere. It just opens the file directly in my Dropbox, and you can download them there if you want. And so I found some very interesting studies and papers that explain how things, how things work for each of the topics. And you just basically go to the readings in the syllabus and you open them. Like for example, for today's lecture, let's see what I have here. So like for example, we have a nice, very interesting paper, by the way, on the sources of 4 commonly reported cutoff criteria. So for Cronbach's alpha, as we talked before, but for also correlation, regression, all of those things. But also there is a very interesting, nice short article about T-scores, Anova, analysis of variance and covariance. Again, with good examples, very good explanation of how they work. But there is one more thing that I want to show you here.
We're not seeing your screen.
Yeah. Sorry. What I was saying is that in the syllabus itself, you have, so in the new syllabus, I sent it to you like a week, 2 weeks ago, but it was not in there on the first day of the semester. So I have the readings lecture here, and you just click on the link, it takes you directly to the article. So you can download them if you don't want to look for them online, because some of them are paid access, and I'm not sure if you have access to them from your home. But so they were very interesting, nice studies, and so they're just basically nice guides. But going back to Tabachnik and Fidel, so what I like about it very much is that, again, if you don't have the book, like for example, Canonical Correlation here. So you literally, if you can see my screen, let me just go speaker view. So after they explain all of the methods and statistics, they have literally how you would write the results section. And I'm not sure if you can read it here. So they literally have text that you would put in the results section. You can literally just copy and paste it and just plug in your names of the variables and your indices. And, you know, like done. Same thing for the regression analysis, same thing for T-scores. And I here, let me share again to show you. On the slide, I gave you the chapter numbers. So if you got that book, and so for each of them, you have the chapters, but also like, for example, regression analysis. You go to page 149 and you literally have, you know, a sample study. And then for that study, they have copies of the printouts, what they would look like in different software. And I think here they use SPSS as an example for that chapter. And then you literally, for that specific study, you have like a few pages of the results section of how you would interpret those differences. And I mean, those results. And, you know, it shows you how you describe your sample and then how you talk about the coefficients and which of the indices from the regression you need to comment on, because some of them, as we did here in Stata, like you get all of these F values and probabilities and within and between residuals. And so you don't know which one you need to comment on. But in that example, you have all you need and you literally just plug in your values and keep the same language. So very, very convenient from that point of view. So they still, you know, Tabachnik and Fidel, they still talk a little bit about the math and they still give you some of the, you know, formulas if you want to know how it's calculated, but it's much more about how to use it rather than, you know, the math behind it. So very convenient. All right, so I wanted to spend also a couple more minutes if you have any specific questions related to your next assignment. So as you remember, now you have to think about a study design that is based either on differences or associations. And so you would need to kind of think about how that study would look like if you wanted to look at the differences between whatever you study, or if there is an association between whatever you study, but controlling for something, or maybe looking at a more complicated picture. So I'm not sure if you have any questions, but that's something we can spend some time and discuss. Next time, once I have your submissions, maybe I'll spend some time looking at the specific examples, but for now I don't have them yet. So unless you want to bring it up.
The due date on that is the 14th.
I think so. You mean the next submission?
Mm-hmm.
Yeah, I think it will be due. Let me see here. So just 1 second. Yes, it is. Assignment 3 is due on March 14. And again, let me share the screen one more time. We will take a quick look at what's expected. Just a second. Yeah, share one more time.
Just so you know, in Canvas, it has the 28th, but the
28?
syllabus
Oh.
says, I think, the 14th. So,
Oh, sorry, my bad. And with your permission, I'll change that right away while we're here. So I don't mind if you need to take a little bit more time. So again, we are past the stage where, you know, it's about deadlines. But my worry is that if we postpone it too much, then it would be, you know, you don't want to postpone it. So oh yes, you're right. It says, so it should be 14, my bad. And I hope, yeah, you recognize that it was, so corrected.
So is this assignment related to our research question that we've been working on, or this is a separate kind of?
No, it's the same question. So
okay.
let's take, for example, I really like that idea of looking at the presence of coverage of the company in the media versus the company acquisition and stock price, for example, right? So let me go back to the syllabus. So we'll take a look at what's assigned, and I'll use that one as an example of the study. So we're looking at the third one, and here you can choose differences and associations. And so you choose one or the other. So describe the study design where you test if there is a difference between two groups, or describe a study design where you are looking at the association between two predictors. And so in my case, it would be probably the association and not difference. So I would want to see if the number of articles about the paper, about the company on day X is correlated with the stock prices of that company on day X. So what I would do is I would get, let's say, for example, you know, for a specific period of time, let's say, you know, 1 month or maybe half a year, I would get the price of the company each day. And then I also would go to Google News and literally restrict the range by date for each day, and would look at how many hits I get in the news for the company, you know, in the news section of Google for the company on each given day. And so I would have column 1, the date, basically day 1, 2, 3, 4, 5. Sorry, not the date, the stock price on each day. You know, one day it was $25, next day it's $24, then it's $26. But then also it would be, you know, like 25 articles about the company on this day, 55 articles on that day. And so I could do a correlation. I mean, that's all I need. But the problem here is that maybe there are some other factors at play. So maybe I want to look at, you know, control for the firm size. And maybe I want to control for, you know, something else here. I don't know, maybe, you know, the weather, or maybe day of the week, or maybe something else, like, you know, whatever the other, you know, factors can be at play. So I would definitely add a couple of controls here. And so, and then probably you want to do it for multiple companies, not just one company at a given time. And so that would be, you know, basically a regression analysis, but with a bunch of controls. Then, go ahead, please.
Voss, one question I have is, do you have a research study that you've, not a research study, but a paper that you've published where you felt you really liked your study design that we could use, or go find that article that you wrote and just kind of see the style that you wrote it up in?
Well, so almost all papers I've done used regression analysis. And so I, you know, just about any paper of mine probably had regression in it. So I can send you a couple of them, but, you know, this stuff, it's easy. Like pretty much every single paper you open, there will be a correlation table. So they look at these, you know, correlation matrix, and regression probably accounts for, I'd say maybe 90–95% of all publications. So it's very, you know, for this one, you don't really have to shop around long. You just get any of those and you just look at the regression and see, you know, what the relationship is. So I've done a couple of meta-analyses where it was more about, for example, discourse. So where we looked at differences between things, or it could be maybe simply like correlations. But for this one, I mean, there are more examples than you can care about. And so there are so many of them. So it's really not something unique. Like once we get to the subsequent topics where we talk about multi-level analysis, for example. So that's where there are a few studies, and I have a couple of those. So that's where the example will be harder to find. So, yeah. So can you give me a couple more topics of yours, and then we will think about how you can design that study. So anyone, for example, does a study where, for example, looking at the difference between two groups will be more meaningful than looking about at associations. Anyone?
Differences between two groups, you're saying?
Yeah. So
two groups over time?
Not necessarily over time yet. So simply, is there a difference between, for example, men versus women, or between, for example, two countries, or maybe two industries? Anyone has anything like that?
Mine is kind of designed like that. At home workers versus in-person working?
Oh, that's a
Yeah.
very good one. Yeah, yeah, right. So one of you is saying that, for example, when you work from home, you have fewer opportunities for promotion, you will be less satisfied, you will have whatever kind of, and so that's a perfect example. So you can have two samples and you can have those who work from home versus those who work from the office, right? And so you can be as simple as, you know, just look at the D-score or maybe run t-test, or you can do, for example, Anova, especially maybe if you have like a third group, maybe you have some combo, like some people work from home, some people work from the office, but some combine the two, like a hybrid. And so you have like a third group maybe, or maybe for that hybrid, you have like low mostly from home or mostly from the office and then right 50-50. So in that case, you probably want to use Anova and you want to have your 5 groups instead of just 2. So that's a very good one. So in that case, you probably want to take a look at differences as opposed to associations. But now, can you turn it into associations instead? Like how would you turn that from differences into associations? Anyone? Like working from home versus working from the office.
The more face time you have, the better chance for promotion or something like
Yes,
that?
so you can use it as a continuous variable and maybe you can look at it, you know, number of days per year that you work from home. And so from some people it may be 0 and for some it may be 1 or 2 or 3 and it can be all the way to 365 for some people. And so in that case you have 2 continuous variables, which probably makes more sense to use than some sort of a regression or some sort of a correlation. And so you would then say, for each additional day you work from home, or for each additional month per year that you work from home, your chances of promotion drop by so many, you know, percentage points or whatever that is, right? So that would make much more sense to do it in that case as association. All right, so you choose one or the other and describe basically the sample, you know, the study design. So you don't really need to get into too much details. You already described your data. You already know what kind of variables you use. You just try to describe it in terms of, you know, what analysis you would do. And so you basically explain how that study would be, sort of how the test will be done. And you just say correlation, regression. But if your data, for example, are not normally distributed, not continuous, then you would say, and for my, for example, relationship, I will have to use either a dummy variable if it's yes or no, or if it's, you know, multiple party affiliations, you'll create a block of dummies. You understand what dummies are and how they work, right? So if you have only 2 categories, then you would have 1 column with 0 or 1. But if you have more than 2, you would have multiple columns and you sort of drop one of them. So it would be sort of your base category, right? And so everybody understands how dummies work. I assume you probably had that in your analysis, but if not, you know, just look it up. It's nothing super difficult. But so that would be what you do here. All right, well, that's all I wanted to cover today. You have a lot of readings, and you know, I don't expect you to read it, you know, mandatory, but I highly recommend that you kind of look at those methods if you missed it. I did talk to Aaron, and he said, and Ayucha, they said that you covered regressions and correlations pretty well in your methods courses. But if you need to look it up, luckily, just any textbook will have something on it. And so I recommend this one, but it doesn't have to be this one particular. So we'll just go from there. All right, well, good night. Have a nice evening. And then, so I think it's next week that you submit, or a little bit more than a week that you submit the next submission, and then I'll give you feedback. And then we will get into more sophisticated things moving on. So we'll talk about moderation, mediation. So when it gets even more complicated than simply controlling for something. All right, well, good night, and see you in a couple of weeks. Bye-bye.
Thank you.
Thanks.
Thank you, Voss. Bye-bye.